We're live on YouTube.
Yeah, it's 8 o'clock, I think.
Yes. Good evening, all. So today we are very fortunate to have with us Dr. T. Ganesh. Dr. T. Ganesh is the chief physicist in Manipal Hospital, Dwarka, New Delhi. Dr. Ganesh was a senior physicist in All India Institute of Medical Sciences. He worked there for many years and then he went abroad and he came back to India and joined Fortis Memorial Research Institute. And I was very lucky to work with him for 4 years in Fortis Memorial Research Institute and learned a lot from him. He is one of my favorite physics teacher. And I must mention that he is the first American board certified medical physicist in India, DABR, and probably the only medical physicist in India who is having American board certification. So I feel everybody, all the students, including me, will get very much benefited by today's class. And Dr. Ganesh, you please now I request you to start the class.
Okay, thank you, Dr. Sayan. Thank you for giving me this opportunity to be once again back with MD students and other physicists here in this meeting. Now, welcome back to this physics class from Kahn's book chapters, and we are going to see, just 1 second, let me share the screen. Yeah. Can you see?
Yes, sir. We can see the screen
Okay. So now
very
we
well
are
visible.
going. Oh, okay. Now we are going to see the chapter number 9. That's about the dose distribution and the scatter analysis in the Kahn's book. So we will now start with, in this chapter, we will be covering about the phantoms, and then we will go on to see about some of the dosimetric functions that we keep every day in our practice, like percentage depth dose, tissue air ratio, backscatter factor, scatter rate ratio. And then finally, at the end of the presentation, we will see how Clarkson method can be used to calculate the dose for irregular field. Now, uh, first of all, we should know, if we have to know about that why dosimetric functions are used. First of all, we have to know that how the photon beam is transported across from the source to the body and how the dose is deposited. A photon beam propagating through air or vacuum is governed by inverse square law. And then when it enters the phantom or patient, let me just laser point. When it propagates through a phantom or patient, it is affected by absorption and as well as scattering in addition to the inverse square law. So while it is propagating through air, only inverse square law and a very negligible attenuation or scattering. And when it propagates through the phantom, it is affected by both absorption and as well as scattering in addition to the inverse square law. Now, these three effects together make the dose deposition in a phantom or for that matter in a patient a very complicated process and its determination a complex task. Now, why phantoms? Why do we have to know about or why do we have to use phantoms? Very simple to tell the answer because the dose measurements in patients is either difficult or it is not possible at all because we cannot go on keeping the chambers or other detectors in each and every point of the patient. So we have to use phantom materials and phantoms that are made up of tissue equivalent materials and phantoms that are large enough to produce full scatter like the way that we will have in patients. What are the basic requirements for a material to fulfill as a phantom material? Phantom should be made of a material that will absorb and scatter photons in the same way as that of the tissue. And the phantom material that we choose should have the same effective atomic number as that of the tissue. Importantly, it should have the same number of electrons per gram, or in other words, the electron density should be same as that of the tissue for the phantom material. And phantom material should also have same mass density, just like the tissue. Most important of all these requirements is about the electron density. The reason is that the Compton effect is actually dependent on the electron density we know. And Compton effect is the most predominant effect in the energies that we use in radiation oncology. So electron density should match exactly that of the tissue. And here you can see here for different materials, what are the electron densities. Mostly it's around 3 or less than 3. And for hydrogen, it is double that. Whereas for the tissue materials, mostly it is around 3 to 3.3. So we need to choose a phantom material that will have the electron density exactly like the uh, tissues. Now, most often we use water as the phantom material. That's because it happens to be the main constituent of the body, and also it's because that it is easily available and also it's very cheap. It's not, we don't have to spend much on the water. However, when it comes to doing measurements inside water, it poses certain practical problems. We cannot freely use the chambers unless otherwise those chambers are water compatible, and several other practical difficulties will be there. So we need to also use sometimes solid phantom materials, and for that we keep using materials such as polystyrene, polymethyl methacrylate, PMMA, wax, rice, and paraffin. So the properties of these materials are given in this table, table 9.1, and you can see here the number of electrons for these material, which are very close to the what we find in the tissue. Now, moving over to dosimetric functions, what is our primary aim? Our primary aim is to know about the dose at different points within this phantom or patient. As I had already told you, it would be impossible for us to keep the detectors at different points inside the phantom or inside the patient in order to know about the dose at these points. So that is the reason that why dosimetric functions are have been developed, because they actually link the known dose at a point. Like this is the known dose at point P to dose at any point which is Q. This Q can be anywhere inside the phantom. So all that we have to know is to just measure the dose at only one point in the phantom P, and then we can determine the dose at Q, which can be anywhere inside the phantom using the dosimetric functions. So dosimetric functions are in use that link the known dose at a reference point to the dose at arbitrary points inside the patient. Now, these dosimetric functions, some of them are valid in the entire energy range that we use in radiation therapy. But some of them are used up to energies of cobalt 60 or less than that, or some of them are valid from cobalt 60 and higher. So what are these dosimetric functions? The dosimetric functions that are used in the entire photon energy range, they are percentage depth dose and relative dose factor or output factor. And the ones that are used up to cobalt 60 energy or below the cobalt 60 energy, they are the backscatter factor, tissue air ratio, scatter air ratio. And the functions that are used from cobalt 60 onward and higher above, they are the tissue maximum ratio, tissue phantom ratio, scatter maximum ratio, TMR, TPR, SMR. In this presentation, we are going to see only these functions, and you will be hearing about these functions in the subsequent lectures. First, percentage depth dose. Percentage depth dose, as perhaps most of you must knowing, it is defined as the quotient. The quotient is expressed as a percentage of the observed dose at any depth D. You see here, this point is at a depth D. So what is the dose here? That is the dose at at the depth D. So dose at any depth D to the dose, observed dose at a reference depth D0. Now this point is at D0. So what is the ratio of this dose to the dose at this point expressed in percentage? And these 2 points are lying along the central axis of the beam. Now, when this reference depth is taken as the peak observed dose, that is when this D0 is taken at D max, where the maximum dose occurs, then that is the percentage depth dose. So many times we call this reference depth as maximum dose or dose maximum or given dose or simply D max. So the dose at this reference point, we call it as by either one of these names. So P is here, DD, the dose at this point, divided by dose at the reference point, D0 expressed in percentage. And when this D0 is at the dose maximum, then we can calculate the dose at the maximum by simply dividing the dose at depth by percentage depth dose multiplying by 100. So just rearranging, we can calculate what is the dose at this maximum point. Now let's see the percentage depth dose curve, how it looks like. Again, most of you must have seen this percentage depth dose. This is the typical shape of the percentage depth dose curve for a 6 MV photon beam, depth in centimeter and percentage depth dose. It rises up to a maximum of 100, and after that there is an exponential decay. So if you try to characterize this photon beam, this is what we get. Actually, we see the dose at surface, and then we see a buildup region, and then we see the depth of dose maximum, and after that we see an exponential fall off region. Let's see one by one. First, the dose at the surface. Now, when we talk about the dose at surface, the first thing that should come to your mind is that it's a very complex quantity to consider and to measure. It's extremely difficult to measure the surface dose accurately. You need very special instruments. There are only a couple of instruments that can measure the dose at surface accurately, and very few hospitals, probably one or two hospitals in the entire country only having this particular device, which is called as the extrapolation chamber. Anyway, that apart, we can confidently say that for superficial and ortho voltage beams, the dose at the surface is 100%. There's no doubt about that. For superficial and ortho voltage, the dose at the surface is 100%. For cobalt 60, 6 MB, 18 MB, typical nominal values are 30%, 15%, and 10% respectively. However, what you have to remember is that when you consider the surface dose from TPS, or even for that matter, these values, you have to be extremely careful to know these limitations, its limitations. You may be off by plus minus 30% or even more than that, depending on the situation, depending on what kind of uh, intervening or modifying devices are used in the beam. And no TPS can accurately calculate the dose at surface. Even the highest end planning system cannot calculate the dose. There are multiple reasons behind that. Reason number one, what you measure, that is what the TPS is reporting. So you cannot measure correctly. So there exists actually the most important uncertainty. Beyond that, in the modeling, so the planning system, when it models, it cannot model in this region, the buildup region, it cannot model the beam very accurately. So there lies the other difficulty. The third difficulty lies in how actually it is calculating the dose in the buildup region, because the dose is calculated for voxels, and when you calculate for voxels have got specific dimensions, and within those dimensions, the percentage depth dose can completely change. So for all these reasons, the dose at surface is an extremely complex quality. Now we see more about the buildup region. We come to the buildup region. The most important question, which many of you might be asking, that why is there a buildup region, which is actually responsible for the skin sparing, the most sought after effect in radiation oncology. We want to spare the skin, and we know that the buildup region is responsible for that. Now, to know the answer, first thing that we have to remember is that dose is deposited in the medium only through secondary electrons. You see that the dose that that we constantly keep talking about, like centigrade, gray, where from does it come? It is nothing but the energy from the photon beam. So the energy from the photon beam, when it is observed, that we call it as centigrade or gray. So energy, how it is actually deposited in the medium, it is deposited in the medium in a two-step process. Never forget this. First, the energy is given by the photons to the secondary electrons. I'm sure that this point would have been mentioned to you in the previous lectures. So the energy is given first from the photons to the secondary electrons. These secondary electrons can be photoelectric effect electrons or Compton effect electrons or pair production electrons. So energy is given first to the secondary electrons, and it is these secondary electrons which in turn actually are depositing the dose in the medium. So the dose that we are talking about, centigrade gray, is actually deposited by the secondary electrons. Now, when it comes to low energy photons, then these secondary electrons will deposit all their energy at the very spot where the photon is interacting. You see here, this is the X-ray. the X-ray is coming here, the black color ray, and it is that interaction point, and at that interaction point, the electron is emitted. When it is a low energy photon, the electron that is emitted will spend all its energy almost at the very spot where it was born. However, when we talk about the high energy photons, these secondary electrons, which are set in motion by these high energy photons, will travel some distance into the medium as they deposit the energy. They don't deposit then and there at that very spot. They travel few, in fact, they can travel few centimeters before they spend up all their energy. And it is this particular reason, or this particular effect, which is the reason for the build-up region. That is, you see here, a photon beam is striking a surface, and what happens at the surface, few photons are interacting and set in motion the electrons. The straight arrows are electrons. And electrons, what do they do in turn? They are producing ionizations. In the first millimeter, they are producing only 6 ionizations. And in the second millimeter, they are producing little bit more, 9 ionizations. And in the third millimeter, they are producing little bit more, now 25 ionizations. And in the fourth millimeter, they are producing 60 ionizations, and by that time they spend up all their energy, and they will die down. So some photons are interacting at the surface, giving rise to few electrons. Some other photons are interacting after traversing 1 millimeter of tissue, then they give rise to some few more electrons. Then some more photons are traversing 2 millimeters before they interact, they give rise to electrons like this. So when you add in the first millimeter, you have got very few electrons, only 6. And in the second millimeter, there are more electrons, more ionizations. So you have got 15 ionizations here. And in the third millimeter, if you sum up all the ionizations, you get 40. And in the fourth, now it is 100. So as you go deeper and deeper, dose continues to build up because we have got now more number of electrons added at each depth. And then it will reach a maximum value D max at a depth of D max, small d max. Small d refers to depth, capital D refers to dose. But it cannot keep on going like this. What happens is that after some time, photons also will start reducing because photons are continuously being, they are interacting, so their numbers will come down. So they cannot give rise to same number of electrons as they do in the initial layers of the phantom. So the number of photons will be reduced, and the number of electrons produced by them also will be reduced, and that is why the dose is now start reducing after reaching the D max. So beyond D max, depth dose will keep reducing. It can also be explained by looking into the Kerma and dose concept. I'm sure, again, this would have been taught to you in the previous classes. Kerma is nothing but the kinetic energy released per unit mass. Remember, in the previous slide, what did I say? This is an important point, a very key point that you have to always keep in your mind, always keep that in the back of your minds. That is, energy from the photon beam is given to the medium in a two-step process. First, energy is given to the secondary electrons, and then the secondary electrons in turn actually deposit the dose in the medium. Fine. So Kerma is all about how much of energy is given by the photons to the secondary electrons. Kinetic energy transferred from photons to secondary particles. Kerma doesn't bother about what further happens to them. I mean, where the electrons are going, which direction they are going, Kerma doesn't consider. And similarly, Kerma is not bothered where they deposit their energy. Electrons, how far they go, how they deposit energy. No, Kerma doesn't take into account. Kerma is just simply representing how much energy has been given from the photon to the secondary electrons. Obviously, Kerma is maximum at surface and decreases with depth as number of photons decreases with depth. How? Let's see this example. See here, this photon beam is entering the medium here at the surface. And let us say that in the first 1 millimeter, 0.1% of the photons will interact. Let's say there are 100,000 photons. 100,000 photons, 0.1%, how many? It will be 1,000 photons. So 1,000 photons will interact in the first 1 mm. So 1,000 photons spend their energy, give their energy to the secondary particles. Fine, that is kerma. Now in the second mm, by the time the beam is reaching the second millimeter or the next layer, how many photons are left out? We don't have any more 100,000 photons. We have only now 99,000 photons because 1,000 photons have already gone. So we have got only, we are left out with 99,000 photons. So 99,000 photons, 0.1% of how much? It is only 990, not 1,000 photons. So that is why if you look at the kerma is maximum at the surface, and as we go deeper and deeper, it starts reducing because number of photons is reducing. Kerma is maximum at surface, decreases with depth because number of photons is decreasing with depth. That is why kerma is maximum here, keeps reducing. However, absorbed dose will keep increasing because the electrons that are set in motion by the photons, they will deposit little further away and they travel mostly in the forward direction. They don't travel backward, they will travel in the forward direction and then deposit. So keeps increasing, but beyond that, after that, they cannot increase anymore because a number of electrons also are coming down due to the fact that the number of photons are coming down. So that is why it starts actually reducing. In fact, if you integrate the area under the Kerma curve, under the absorbed dose curve, they will be perfectly equal. When you take it to the infinity, when you integrate, they will be perfectly equal. What has been lost here actually will be made up by the absorbed dose here in this region, slightly increased, right? So now we come to the depth of dose maximum next. That is the next characterization of the percentage depth dose curve, where the dose maximum occurs. The value of the maximum dose called as the capital D max occurs at a depth D max, small d max. So it occurs at the surface for low energy beams, and as the energy increases, it occurs more deeply. You can see here it occurs at surface for low energy beams and then at deeper as the energy is increased. And it is approximately equal to the range of the secondary electrons that are set in motion. Now, the depth at which the dose maximum occurs, that depends on the field size. As a simple thumb rule, as the field size increases, the D max will decrease. You see here, the field size is increasing, the depth at which the maximum dose occurs keeps reducing. For 6 MV, it is like this. For 10 MV, here it is maximum around say like 22 mm, but as the field size is increased, it is now 18 mm or 19 mm. And for 18 MV, here it is maximum 35 mm, but as the field size is increased, it keeps on reducing at now the maximum occurs at only 25 mm. So as the field size increases, the depth at which the dose maximum occurs will decrease. And why? The reason is due to electron contamination. Because when the field size is larger, there is electron contamination occurring from collimator, from the intervening air, and also from the flattening filter and many other sources. So electron contamination occurs, and this electron contamination will actually spoil the depth of the dose maximum. Though the depth at which the dose maximum can actually keep on decreasing with the increase in field size, the magnitude of the dose maximum at that depth will increase with field size, right? So we will see about that in the next slide. The magnitude of the D max will increase with increase in the field size. So that is a different thing. You see here, as the field size increased, see here from the field size is from 3 by 3 to 40 by 40. So the magnitude of D max will increase with field size. So this is what called as the output factor or output. Output will keep on increasing. Here output means how many centigrade per 100 monitoring unit. For a 10 by 10 field, if you look at this graph, it is 100 centigrade per 100 monitoring unit. How does it increase? From 3 by 3, it is 86, 10 by 10, it is 100. But then 40 by 40, from 3 by 3 to 10 by 10, 14 increase, 14 centigrade increase. But from 10 by 10 to 40 by 40, such a large increase in the field, the increase in output is only 11 centigrade, 111 centigrade. So why does it flatten out at large field sizes? There is a reason. See, physics, actually, you have to ask yourself question, why, how? If you dig out the answer, then physics becomes not only interesting, but also easy to understand. If you just take it at the face value, then it becomes very difficult to comprehend. But if you go deeper and try to find out the answer, the subject not only becomes interesting, but also for you, it becomes easy to remember things, and also later on, at different context, you will be able to comprehend the things very easily. Why does it flatten out large field sizes? Let's see this example. You see here, first let us take this smallest field size, take the center. From here, the field size is increased to here. You see here, the field size is increased. Now what happens when the field size is increased, the scatter coming from this newly included region are able to reach this center point. Fine. So all the scatter radiations that are arising in this newly included region are able to reach the center of the point, which is our point of interest. When the field size is further increased, sure, now furthermore, large amount of area has been included. However, not all the scatter that is originating is able to reach the center point. As against the 8 arrows, we are seeing only 5 arrows here. So other scatter radiation starting from here, they are not able to reach the center point. Now, when the field size is further increased, only very few scatter radiations are able to reach the center. And this is the reason that why actually the output flattens out at large field sizes. Initially, as the field size is increased, more scatter from the increased region can reach the Dmax, but as the field size is further increased, the scatter from the outermost region will not be able to reach the center, and that's the reason that why it actually flattens out. Now comes next is the attenuation region. Past the Dmax, the dose is decreasing due to exponential attenuation of the photon beam. More and more photons are removed from the beam. The attenuation of the beam, reason number one. And reason number two, inverse square law. Remember, in the initial couple of slides, we saw that when the photon beam is passing through the air, it undergoes inverse square law. And when it enters the phantom, there also inverse square law will play. So the past the Dmax, there is an exponential attenuation. The dose decreases due to exponential attenuation and as well as the inverse square law. Please do not forget, because all these factors will play important role in the dose functions that we are going to see. Even though the dose may be decreasing, scatter component is increasing. This is another key point. One key point is that inverse square law you cannot avoid. Another key point is that even though the dose may be decreasing as you go deeper and deeper, the scatter component is increasing. Do not forget that. This will give you a lot of answers to many practical problems. So we are going to see some of the examples. PDD is dependent. We have seen about the PDD, how we can characterize the percentage depth dose curve. PDD is dependent on what are the factors: energy of the photon beam, the depth of the point of interest, the field size on the entry point, that is on the surface of the phantom or surface of the patient, and source to skin distance, which is called as the SST. Now, first, PDD is dependent on the energy. It will increase with energy and it will decrease with depth. As you can see here, as the depth increases, the percentage depth dose decreases. So it decreases with depth and it increases with energy. You see here, as the energy is increased from cobalt 60 to 4 MV, PDD at a given depth increases, and from 4 MV to 10 MV, further it increases. At the same depth, when it is increased to 25 MV, it is further increased. So it increases with energy, but decreases with depth. Higher energy beams have greater penetrating power. So this happens because with increase in energy, the higher energy beams have got greater penetrating power, and that's the reason that why we get higher PDD at a given depth. Fall in PDD for different energies per centimeter of tissue, you must remember. Again, just like the key points, there are certain thumb rules which you should not forget. Whenever you want to practice, you have to have this in mind. For cobalt 60, in the initial depths, that is at shallower depths, for every centimeter of tissue traverse, the fall in PDD is about 5%, whereas at deeper depths, the fall in PDD is only 2% per centimeter. See, initially 5%, every 1 centimeter, it will fall by 5%. But as you go deeper and deeper, for every 1 centimeter, the fall in PDD is only 2 percentage per centimeter. Whereas for 18 MV, shallower depths, the fall in PDD is 3%. And as you go deeper and deeper, even at large depth, for every centimeter traversed, the fall in PDD is only 2.5%. See the vast difference between the cobalt 60 and 18 MB. Do not forget these. These are some of the thumb rules that you should not forget. Now, these are the percentage depth doses for cobalt 60, percentage depth doses for 18 MB photon beam for different field sizes. And you can see here the PDDs are noted down for square fields. Fine. Effect of the field size. As I told, the periodic data are normally tabulated for square fields starting from 4 by 4 to 40 by 40 for different depths. These are the different depths, and these are the different field sizes, and for different field sizes at different depths, what are the PDD values that are given. And for a given depth, as the field size is increased, you see here 10 centimeter depth, as the field size is increased from 4 by 4 to 5 by 5, the PDD increased. So as the field size is increased, the percentage depth dose increases, and this is due to the increased scatter. Now the question is, does the shape matter? Because in the previous slide we saw that the PDDs have been tabulated only for the square fields. Now if it is a rectangular field, does that shape matter? Of course it does matter. You see here, the square fields and elongated rectangular fields having the same area would have different PDD. Look at this graph. This is a PDD graph, sorry, the out percentage depth dose PDD for different areas. 10 by 10 square field. You see here, this square 10 by 10, how much is the value? Something like 31 or something like that. And for 20 by 5, both are having the same area. 10 by 10 area is 100, 20 by 5 area is 100. However, for 20 by 5 the PDD is slightly less than 10 by 10, right? That is what I mean by this statement, that the square fields and elongated rectangular fields having the same area would have different PDD. The rectangular field will have lesser PDD and the square field will have higher PDD. Why? Here we can see, this is the square and this is the rectangle. Both have the same area. You see the shaded area, that shaded area is common for both rectangle and as well as for the square. But in rectangle, these areas are now put just above this shaded area in the square. So both these areas, rectangle and the square, they are one and the same. Area is one and the same. However, now the scatter radiations from this, because they are very close to the center, they are able to reach this point. However, scatter radiation that are originating here, the center point is at a far away distance, so they are not able to reach. The red arrows are not able to reach. The green arrows are able to reach. So as against the 8 arrows, now only 4 arrows are reaching the center point. 4 arrows are lost. So that is the reason that why PDD for rectangular field is lesser than the square field having the same area. So that is why we have developed a concept of equivalent square. From this tabular column, you can see here the long axis and the short axis, like 10 by 26, you can say that that is 13.7 or 13.8, like this 10 by 28. So you can find out the rectangular field size and find out what is the equivalent square of the rectangular fields. Or you can also use this formula called as the equivalent square of a rectangular field is 4 times the area by perimeter, 4 times into A by P. Now dependence on SST. PDD increases as the source to skin distance increases, and that happens due to inverse square law. I told you, never forget the inverse square law. Now, when the source to skin distance increases, the PDD will increase, and that happens due to inverse square law. How? Again, I told you, always ask how, try to dig out more and try to find out the answer. And once you know, then you will find that physics is interesting. You see, from moving from this maximum dose to this point of interest, what happens for the beam? The beam suffers two things. One is attenuation by the medium. You see here, this depth, it is going to attenuate the beam. But for a given depth, this attenuation will remain the same for any SST, whether SST is small or large. This attenuation is going to be same because we are considering a depth D. So D is same for both SSTs. So attenuation by this depth will be same irrespective of the SST. However, reduction by inverse square law, this factor will vary according to the SST, because this inverse square law factor will vary depending on the SST. How? Let's see an example. SSD 10 centimeter. Don't ask me whether it is possible or not. This is just to highlight how this happens. So this is just only an example. SSD is here 10 centimeter and SSD here is 100 centimeter. Fine. And we are considering a point which is at 10 centimeter depth, and this is the dose maximum, and we are considering a field size 10 by 10. So this red horizontal line, that represents the field size. Field size at 10 centimeter distance, same, and 100 centimeter field size is same 10 centimeter. And we are considering at the same depth. What is the inverse square law? D max is 1.5. Let us say that this is for 6 MB. So D max is at 11.5. So 11.5 by 20, because 10 plus 10, 20. This point is at 20 centimeter from the source, whereas this point is at 11.5. So inverse square law is 0.33 for this geometry. Whereas for this geometry, inverse square law is 0.851. If you calculate 101.5 divided by 110 the whole square, it is 0.851. So inverse square law is higher for larger SST. And similarly, we take another example, 80 centimeter, 100 centimeter. If you substitute the values, once again, you can find here it is inverse square law 0.82, and here the inverse square law is 0.851. Howsoever small may be, the bottom line is that as the SST is increased, the inverse square law factor will increase. And that is the reason for the increase in PDD when you increase the source to skin distance. Now, question is how to calculate the new PDD when the SST changes from F1 to F2. Generalized condition, not any specific example. So from F1 to F2, if we are going to change the SST, how to calculate the new PDD? So this is the case. For F1, we know the PDD at this depth D centimeter, and we want to treat the patient at the new SSD F2, and we want to treat the same depth and same field size, like 10 by 10 field size treated at say like 100 centimeter, 10 by 10 field size, we want to treat the patient at 150 centimeter. So what is the new PDD? How to calculate? If we just write down the equation, I'm not going into the details how we can obtain, but it is just simple mathematics that the PDD at F2, PDD at PDD at SST F2 divided by PDD at SST F1, PDD for F1, the ratio of these two PDDs is simply the inverse square law stated here. And this factor you can see here is simply nothing but the inverse square law. And that is denoted as what is called as the F factor, or simply called as the Maynard factor. If you look at this equation, you can simply say that, you can easily say that when F2 is larger than F1, then F also will be larger than 1. But when F2 is smaller than F1, then in that case, according to this equation, F will be smaller than 1. Fine. So this again you have to remember. But the Maynard factor F actually overestimates the change in PDD with change in SST. So we can say that we can, when we change the SST from 100 to 120 or 100 to 70, we can use this formula, we can calculate, but the change in PDD when calculated using this formula or using this factor will actually overestimate the change in PDD. Okay, so Maynard factor F overestimates the change in PDD with change in SST. Question why? Again, once again, remember, you ask, when you ask and when you try to dig out the answer, you will actually develop more interest towards the subject. Now, before we answer this question, I would like to ask you another question, right? Probably some of you might not have seen this. These are the wedge isodose curves. Fine. Let's have a look at the isodose curve. Some of you might have definitely seen, many of you might have seen that. Now let us look at the 80% isodose line. How much is it tilted? See here, this 80% isodose line is tilted by an angle theta, which is nothing but the complement to the angle that this 80% isodose line subtends with the central axis depth curve. Complement of the angle that is subtended by the 80% isodose line with the central axis depth. Now look at the 40% isodose line. How much is this isodose line tilted, right? Question is, are they tilted by the same degree? Just for comparison purposes, a parallel line to that of this red line, I have given this red dotted. Okay, if the 40% isodose line had it also been tilted to the same one, we can say that they are tilted by the same degree. But here you see, here there is a big difference. 40% isodose line is not tilted to that extent that the 80% isodose line has been tilted, right? Wedge, so the bottom line is that wedge isodose curves aren't tilted by the same degree. Why? The answers for both these questions are one and the same. Maynard factor F overestimates the change in PDD with change in SST. Why? For this, you have to know another key point. Once again, these key points, when I say that these are key points, never forget that. These will come in handy for you to understand many of the concepts in radiation oncology physics. So dose at a given point in a phantom has got two components. One is primary and another is scatter. As the depth increases, the scatter component is more and the primary is less compared to shallower depths. You see here, as the depth is increasing, the scatter fraction is also increasing. And the primary fraction keeps on decreasing, right? And it is more so for the low energy like cobalt 60 beam. And for larger depth, you see here, as we go deeper and deeper, the scatter component is increasing more and more, and the primary component is decreasing lesser and lesser. And for larger field sizes, you see here the field size is 20 by 20, and this increase and this decrease will be more for 25 by 25 or 30 by 30. So this is the reason for both the questions that we just saw. The Maynard factor F is based on inverse square law, which is applicable on primary component only, right? Inverse square law is applicable only for the primary component. Inverse square law has nothing to do with the scatter component, because scatter remains largely unaffected by change in SST. Not largely unaffected, they are not affected by change in SST at all. It is, however, this factor that scatter component is not affected by change in SST has not been taken into effect in F. In Maynard factor, we just assume that everything is just according to inverse square law, which is not correct. That is why the Maynard factor overestimates. And similarly, wedge isodose curves, if you look at that, the wedge effect is entirely due to the differential attenuation of the primary beam across the wedge, be it physical wedge or dynamic wedge or motorized wedge, whatever the wedge may be, the wedge effect is entirely due to the differential attenuation of the primary beam across the wedge. And the wedge will not affect the scatter component. And at shallower depths, where the primary component is more, the tilting is more pronounced. So here, the primary component is more, shallower depths. So the tilting effect is more by the wedge. But however, at deeper depths, the scatter component is more, primary component is less. So this same wedge, which was able to tilt the isodose curve much more effectively at shallower depths, is not that effective at increased depths, at deeper depths. So now we move on to source to axis distance setup. That is all about the PDD. So now we move on to source to axis distance setup. SAD setups are often used in the treatment of the deep-seated tumors with multiple beams or with rotational beams. Now, in comparison with the constant SST setup that relies on PDD distributions, because when you are setting up the patient by SST technique, you have to use the PDD. But when you are using this source to axis distance setup, SAD setup, then you cannot use that PDD. You can use, but it will become more cumbersome. So for SAD setup, which is more practical, which is more easy, then uh, this setup relies on other dosimetric functions like tissue air ratio, tissue phantom ratio, tissue maximum ratio. These two you will see in the subsequent lectures. We are going to see the tissue air ratio. The tissue air ratio was developed by Harold Elford Johns, H.E. Johns, the person, the scientist, the physicist who actually developed the first telecobalt unit in the world in the 1950s in Canada. Saskatoon, he developed the first telecobalt unit. So this tissue air ratio concept was developed by him to simplify the dose calculation in rotational therapy. And also it can be used for multiple stationary beams such as like this. You can see here anterior and posterior beams, and then two parallel opposing right and left lateral fields. So the target volume is at the isocenter, and the SSD varies from one beam to another because of the change in the body contour. So SSD will be different for each of these beams. However, the SAD will remain constant for all the four beams. It will remain constant. So this is the diagram for tissue air ratio. Tissue air ratio is nothing but the ratio of the dose at a given point in the phantom to the dose in free space at the same point. You take the point here, that is at a depth D. So it is inside a phantom. So what is the dose at this point you measure? And what is the dose at the same point? See this geometry. Geometry you should not forget. Source to point distance is same in the phantom and as well as in air. So what is the dose here inside the phantom? For this point, which is lying at a depth of D, measure, and then what is the dose to this same point in air, you measure the ratio of this to this value. That is the tissue air ratio. In PDD, we took the same ratio but expressed it in percentage, but here we just take it as ratio only. We do not express it in percentage. Fine. The point is at the same distance from source. Do not forget this. And field size is same. So the field size here is same. Field size is same here. You cannot alter this. So to don't try to understand the PDD and the tissue ratio separately. Do not draw, but actually always draw the setups together. Means do not forget the geometry. So the source is at the same position, but in SAD setup, the point is closer to the source. So here it is at a depth of D, and here it is in air. The ratio of dose at this point to the dose at this point, that is the tissue air ratio, which is at the same distance from the source. But however, PDD, the points are at different distances. PDD, it is the dose at this point to the dose at this point expressed in percentage, right? So these 2 points are at different distances, but the field size here, here, and here, field sizes are same, but the points are at different distances for SST and for SAD. Now, this geometry tells us one more thing, very important, very, very important, that you have to again always keep in mind. When it is TAR or tissue air ratio, only there is attenuation and scatter. See here, this point doesn't have any scatter, but whereas this point has got scatter, and it has got attenuation due to this intervening thickness. So in tissue air ratio, we consider only the attenuation and the scatter. Whereas in PDD, same attenuation is there, scatter is also there. In addition to that, there is inverse square law because the points are at different distances from the source. So in PDD, inverse square law is an additional factor. In TAR, it is not. So now comes another important difference between the PDD and the tissue air ratio. PDD is dependent on energy, it is dependent on the field size, it is dependent on the depth, and it is also dependent on the SST. We had already seen all these things, but tissue air ratio, while it is dependent on the energy, field size, depth, it is not dependent on SST, it is independent of SST. Now question is, how can that be? Here comes another interesting question. How can that be? Look beyond Kant's book. You see, Kant's book is not the last book that you should refer to. You have to look beyond Kant's book. So these are some of the excellent books that you should read. So this is Fundamental Physics of Radiology by Meredith and Massey. This is the Physics of Radiology by Johns and Cunningham. And this is the IAEA book from Podgorsk. So all these books can teach you a lot of important things. In fact, I would say that if there was ever a book that was exclusively written for doctors in easy language without much of equations, I would strongly recommend this Fundamental Physics of Radiology by Meredith and Massey. Every one of you should go through if you have to understand the physics in a easy way. The language is extremely simple. So this is the most important book. Now come back to that question. TAR is independent of SST. How can that be? Now consider SAD 100 centimeter and SAD infinite centimeter. Source is at infinite distance. You see here, this is the source and the beam is divergent, and here this is SAD 100. You see, from here to here, SAD equal to 100, this divergent beam. On the other hand, when the source is located at an infinite distance from the phantom, when it is infinite, what does that mean? That means that there is no more any divergence, because at infinite distance, the rays will become parallel. You cannot notice the divergence. That is why the edges here are straight here like this. So for infinite beam, the edges are straight. For SAD 100, you can see the divergence. Fine. So TIR comprises only attenuation and scatter. Whether it is for 100 centimeter or whether it is for infinite centimeter, the attenuation and scatter will, we have to consider only attenuation and scatter, because in the previous slide only we saw that TIR comprises only attenuation and scatter. There is no inverse square law coming into picture. Attenuation is same in both the cases, because attenuation is going to be produced by only this. This is the point of interest Q, and above Q there is a depth of D tissue lying above this point of interest Q. Fine. So depth equal to D for both SSTs 100 and as well as infinity. source. But what about the scatter at Q? For that, we have to consider the beam divergence. For SAD 100, this trapezoid, that is the area from which, or volume from which, the scatter is going to reach Q. I hope you will agree to this, because this is the volume being irradiated by this divergent beam, and this is the volume from which the scatter is going to reach point Q. Now take SAD equal to infinite centimeter. Now that is the yellow shaded area, and from here the scatter is going to reach point Q. And if you look at both, for the divergent beam, this area we are missing. However, this area, this red area is added up. And for yellow, we get added region here, these two triangles, but the yellow region is missing out on these red triangles. See, however, whatever that has been lost here, that has been gained here, and vice versa. In other words, both volumes are one and the same, and hence scatter will also be same at the point Q. And this is the reason that why tissue air ratio is independent of SST. And for that factor, or for that matter, in your subsequent lectures, you are going to hear the TMR and the TPR, they are also independent of SST because of the very same reason. Now, TIR and energy. The concept of the dose to small mass of medium is not recommended for beam energies above cobalt 60. So we don't have to talk about the dependence of TIR and energy, because this dose to free space or dose to small mass of medium in free space is not recommended when the beam energies are higher than cobalt 60. Consequently, the concept of TIR is not used for higher beam energies above cobalt 60 gamma rays. TIR and depth, as the depth increases, TIR will decrease, just like we had seen with the case of percentage depth dose. As the depth increases beyond D max, the TIR also will decrease. And with increase in field size, just like in PDD, with the increase in field size, the TAR also will keep on increasing. As you can see here, this is the side of the equivalent square, and as the field size is increased, the TAR is also increasing, and these different curves are for different depths. So whatever be the depth, as the field size is increased, the TAR value is increasing. Now come to the backscatter factor. Backscatter factor is nothing but a special case of the tissue air ratio, ratio of the dose at the reference depth of maximum dose in the phantom to the dose in free space. You see here, this is tissue air ratio. Tissue air ratio, this point is at any arbitrary depth D. So dose at this point to the dose in free space, that is tissue air ratio. But when this depth is at the D max here like this, then tissue air ratio becomes the backscatter factor. So backscatter factor is equal to dose at D max divided by dose in free space, both at the same point. Or BSF is nothing but a tissue air ratio at the maximum dose depth. So BSF, like TAR, is independent of SST, and it depends on the energy and field size. For orthovoltaic beams, it can reach up to a factor of 1.5, which means that whatever dose here at the maximum, that which is at the surface, it can be 50% higher, 50%. So forgetting about the BSF can introduce a huge error in orthovoltaic beams. However, for cobalt 60, for 10 by 10, the backscatter factor is just only 1.035 or 3.5%. Both PDD and TIR tell us how the beam is attenuated within the phantom. The only thing is that, as we had seen in the previous slides, PDD has an additional factor of inverse square law in it. Obviously, they are related to each other because they tell us same thing about the attenuation of the beam within the phantom, within the patient. One tells about additionally inverse square law, but however, both are talking about the same. So PDD and TAR are related to each other by this equation, And also you can find out from one SST to another SST, you can go. Earlier that was the Maynard factor. In addition to that, if you use the tissue air ratio, ratio of tissue air ratios, then Maynard factor, that overestimation can be brought under control. How tissue air ratio, we can see a practical example how it can be used. For example, this patient we have to treat by a rotational therapy for a centrally located target volume. So all you have to do is to divide this contour into in 10 degrees or 20 degrees. You see here 0, 20 degrees, 40 degrees, 60 degrees, and at along each radius you just measure what is the depth. See here for 0 degree depth the radius is 16.6, for 20 degree it is 16, but here for 80 degrees it is 9 centimeter depth, and for 100 degrees it is 9.4 centimeter depth. So you divide the body contour into multiple sectors like this, and at each angle what is the depth you measure, and for that depth find out the tissue air ratio. So tabulate like this. So in total you will find 18 depths, and for 18 depths when you add all the tissue air ratio, this is the value that you get, 9.692. So the average tissue air ratio is 9.692 for divided by 18, 0.538. So 0.538 is the average tissue air ratio for this particular setup. And then from you want to give a dose of 200 centigrade to the target volume, and the tissue air ratio is 0.538. So the dose in free space is 371.8, and if the dose rate in free space is 86.5, you have to switch on the beam for 4.3 minutes in order to treat that particular case. Now, another key point, you cannot separate the primary and scatter. Now consider a phantom that is being irradiated by a photon beam. The dose is deposited by a strong shower of primary photons and scattered photons. All along this volume, the dose is deposited by the primary photons, the secondary particles that are set in motion by primary photons, and as well as set in motion by the scattered photons. Scattered photons means the first scatter, second scatter, and the third, fourth scatter, like that. A photon can be scattered multiple times. So the dose is deposited by a strong shower of primary photons and scattered photons. And there is no instrument in the world which can separate the primary photons and the scattered photons. So just like you cannot separate once you once you mix the milk with water, you cannot separate the water from milk, and similarly here also you cannot separate the primary photons from the scattered photons, vice versa. However, it is always preferable for us to compute the primary dose and scattered dose separately. That will be of help in several clinical situations, particularly for calculating the dose to irregular fields. When we are dealing with dosimetry of irregular fields, it would be quite helpful if we can separate them out, primary separate, scattered separate, right? And that is where the scatter air ratio comes into picture. The scatter air ratio is nothing but the ratio of the scattered dose at a given point. It is not possible to measure this scattered dose alone. You just cannot do. You have to only calculate, theoretical calculation. So scattered dose at a given point in the phantom to the dose in free space at the same point, that is the scatter air ratio. So scatter ratio is just like TAR. It is independent of SST, but is dependent on energy, depth, and field size. And scatter area ratio is given by TAR for a particular field size at depth, and for a particular field size RD, minus tissue air ratio at the same depth for field size of 0. So there is no field size 0, but that's how we calculate actually. The primary component we calculate in this way. So SARs are tabulated as functions of depth and radius of a circular field. This is different from TAR and PDD, which are tabulated as a function of square fields, but here they are tabulated as a function of circular fields. So we come to the last part of this presentation, Clarkson method. How much time? Oh, sorry, I have already taken 1 hour. So irregularly shaped fields are commonly encountered, and dose functions like PDDs, TARs, TMRs cannot be used to calculate the dose here. And for non-square fields, if they are rectangular square fields, then it is easy to calculate them, very simple. But when it comes to irregular fields, it becomes quite difficult to calculate the dose at irregular fields. Like here, the mantle field, we want to calculate the dose at Q. So the method suggested by Clarkson is that you divide this irregular field into several sectors of circular fields. You see here, there are 36 radii, right? 36 radii. Sector 1, Sector 2, Sector 3, Sector 4, Sector 7, 8, 9, like that, so on and so forth, up to Sector 36. Now, this particular sector has got a radius of R1, and here it has got a radius of RA. So you can divide it to either 10 degrees or 5 degrees or whatever that degrees that you want. So the principle, the basic principle is like this. Yeah, I'm going to share this PPT in a PDF format later on with you. You can go through this. The this figure is given wrongly in Con book. So this I have taken from the IAEA book. So you see here, what is the scatter that is reaching Q from this shaded area? Now draw a circle like this. You see here, draw a circle like this. For this uniform circular field, this sector would be contributing 1/36 of the scatter air ratio for this circular field. Agreed? And now this shaded area is also in this irregular field. So how much it would have contributed in the circular field? Same amount of scatter it is going to contribute at Q for the irregular field also. So just find out 1/36 of scatter air ratio for R1. Similarly, you do for R2, R3, R4, R5, like that. But when you come to R7, there is a problem. What is the problem? See, this is actually lung shield. You see, lung shield. So scatter from here will reach Q, scatter from here will reach Q, but scatter from here will not reach Q. So for that, what you do, all you have to do is to first take into consideration this entire circle RA, find out that is the total sector. From that, you subtract RB, that is the first inner circle, you reduce, then you will take into consideration only this area. But you have to add this. So add the innermost circle. So take first the bigger circle, subtract the first inner circle, add the innermost circle. In that way, you will be able to actually account for this area and avoid this shaded area. So that way you can actually sum up all the 36 sectors in order to get the total tissue air ratio. So total tissue air ratio equal to TAR for 0 and plus the scatter air ratio averaged out for all the 36. Not averaged out, summed up of all the 36. So to summarize, we have seen about the phantom types, their requirements and their uses, and also we had seen the relative dose functions like percentage depth dose, tissue air ratio, backscatter factor, scatter air ratio. They are all used in dose calculations. Ratios are ratios expressed in percentage. They relate the dose at a reference point to any point in the phantom or patient. PDD, TAR, BSF, SAR are used up to cobalt 60 energy, and PDD, TMR, TPR, SMR are used in the MV energies. You can ask your questions later on to my email ID. This is my email ID, sptgnadar@yahoo.com, or you can also WhatsApp questions, your questions to 9899117811. You can find my PowerPoints in the following link. I will be loading my PowerPoint in the PDF format into this link. If you just WhatsApp me, I can share you this link through WhatsApp. And in the above link itself, as and when you post your questions, I will try to post my answers, and the question and answer sessions will keep getting updated as new questions are received from you. We will again meet another interesting topic on October the 8th with an interesting topic, electron beam therapy, right? That is the 14th chapter. Thank you very much. And if I
Th-
have got any questions, I'll be very happy to answer
Yes.
them.
Thank you very much, sir. We are really grateful that you have agreed to take 3 classes, and your class is always a feast. And to be quite frank, this is for the first time I understood Clarkson segmental integration. I tried to understand it many a times, but this is for the first time I understood that. It was a very difficult topic, but very important topic, and you explained so nicely and in a lucid manner. We have many questions, sir. We have many questions in Q&A. Dr.
Yeah,
Deepak, will you be taking the questions?
Yeah.
Yes. Okay.
So thank you very much, sir,
yeah,
for
yeah.
your excellent presentation. So the questions, kindly explain further on dose modeling by treatment planning system. Um,
Dose modeling by treatment planning
treatment
system.
planning system, yeah.
It's a long lecture by itself. See, the thing is that you have to measure, do certain measurements and feed it into the planning system. And then planning system will develop what is called as the dose kernels based on several fundamental physics principles. See, how the energy is deposited from the photon to the medium, the entire radiation transport is modeled by the TPS, and that's what we call it as TPS modeling. It's a very complicated subject, and it requires a full lecture, perhaps a couple of lectures.
Yeah.
Hmm.
So the next question is, if as the voxel is a very small area, would PDD within a voxel be a concern?
Mm-hmm. Oh, no, I don't think, but there will be certainly attenuation. Actually, I had some other slides, but for want of time, I had skipped that. Um, the Within a voxel, there is about 0.6% attenuation of the photon beam. In a typical voxel of 2.5 mm by 2.5 mm by 2.5 mm, there is an attenuation of 0.6% or scattering of 0.6% of the photons. So PDD will not differ that greatly, especially with the high energy photon beams, but that they are all actually handled by the planning system.
Okay. So the next question is, why does different photons start interacting or produce secondary electrons at different depths? Why don't all of them start interacting at surface?
Good. In the previous classes, I happened to listen to what is called as the Q&A sessions. So in 2 or 3 of the classes, the question, one of the repeated questions that were asked to the teachers was that uh, why the Compton effect increases with energy, right? I had slides, but for want of time, I did not show. You have to know that interaction of radiation with matter, the photon interaction is a statistical process. See the key point, the interaction of photon with matter is a statistical process. A photon can interact right on the skin, or a photon can traverse through 2.5 meters of concrete through and through without interacting, not even a single interaction. It is a statistical process. So which photon will interact, which photon will not interact, we cannot say. It is a statistical process, and statistical processes can be explained very nicely by certain observations like attenuation coefficient. So we measure and we can explain the statistical processes, but we have to know at the end of the day that photon interaction is a statistical process. If you take a particular photon, we cannot say that when it is going to interact. All we can say is that they will interact according to attenuation law. And that is the reason for the increase in Compton effect also. So as the energy increases, the probability of Compton effect increases, and the probability of photoelectron interaction is decreasing and comes to 0. And the pair production, it will start increasing. It's all probability. So it's just simply the probability. If we toss the coin, 50% of the time it comes head, 50% of the times it comes tail. Can we explain why? No, there is no answer. But we can observe it and we can record it. And that's what it happens with the interaction of radiation with matter also.
Okay. So he has asked few many more questions, the same person. So just to say, he says whether if depth of energy of beam increases or intensity decreases. Also, he wants to know what decreases with the depth. It's the beam energy or the intensity.
Oh, that is another good question. As far as the photon beam is considered, good question. Do not forget this fact. If we are considering a 6 MV beam or a 10 MV beam or a 15 MV beam or for cobalt 60, as we go deeper and deeper, the photon energy spectrum does not change, or there is very hardly little change, right? So the energy spectrum of the photon beam doesn't change as you go deeper and deeper, but that is not the same in electron beam. With every millimeter of tissue traversed in electron beam, energy of the electron beam will continuously change, but not in the photon beam. So it is the energy that is given from the photon beam to the medium that keeps on decreasing as we increase the depth, as the depth is increased, but the energy of the photon beam doesn't change at all.
Next question is that if the secondary electrons are mostly forwardly scattered, how does electron produced at edges contribute to the dose measured along central axis?
The electrons that are produced at the edges cannot contribute to the dose at center. What I said, these are the scattered photons. You see, electrons, once they are produced, they can travel at the most a few centimeters only, depending on the energy of the energy transfer from the photon to the electron, right? Maximum 2, 3, 4 centimeters, not more than that. But scattered photon, a photon can get scattered from the edge of the beam, and that photon can come back to the near the central axis, and that scattered photon in turn can give rise to another electron. It can interact. The scattered photon can interact with the medium and can set in motion another secondary electron, and that's how it can contribute to the dose in the central axis.
Next question is, why do we keep SSD at 80 centimeter or 100 centimeter in clinical practice?
That's for the simplicity purpose, because the PDD, we cannot keep on measuring the PDDs for the many 80, 81, 82, like that we cannot keep. We have to keep one standard distance, so that, and also it is important for the practical point of view. If you have got different SSTs that you are going to treat the patient with, then actually you will end up in a big mess. You will be creating a lot of opportunities for error creeping in.
So another question related to SSD is that when should we plan based on SSD and when SAD?
I think it's very simple. When it is a single field technique, when you are treating for some palliative cases and shallower depths, say like up to 5 centimeter depth or up to 6 centimeter depth, provided there are no any extremely critical organs that are lying underneath, you can treat by single field SST technique. But otherwise, for all other techniques, you should go in for only SAD technique. Use of SST is very limited, and that's only for palliative cases, I can say, and for electron beams.
Next is that what is the clinical or physical significance of backscatter factor?
As I said, for cobalt 60, I told you for a 10 by 10, the backscatter factor is 1.035. That's about 3.5%. But the same thing, if you are measuring for 6 MV or 10 MV, it will be less than 1%. So backscatter factor is not important. So that is why it is not used in the, you see my third or fourth slide, I had mentioned that some of the factors are not used in the high energy. So they are used only up to cobalt 60. So backscatter factor almost loses all its importance in the high energy spectrum or high energy photon beams.
Sir, for a manual planning of mental field of for Hodgkin disease, do you apply this Clarkson principle manually, or how do we do it?
Yeah, ideally you have to do it that way only. Manually, you have to draw whatever I had shown. That is the correct picture. That same picture, even though it has been given in the Khan book, it's not correct actually. This particular picture has been taken from the IAEA book, that Podgorsk book number 3, which I had mentioned in my slide. And you have to do it manually. Yes, you have to draw that mantle field, everything on a graph sheet, and then you have to calculate that way only, provided you have got the scatter air ratio data with you.
The next question is why PDD decreases with depth?
That's because I told, because as you go deeper and deeper, the beam is getting attenuated. There are less number of photons left out in the beam. So less number of photons will give rise to less number of secondary electrons. So less number of secondary electrons will contribute or deposit energy, less energy. So that is why compared to the energy at that depth, compared to the energy at the Dmax, the dose at deeper depths is less.
Next is why TAR is not applicable for energies more than that of cobalt-60.
You remember, you see that tissue air ratio, it's the ratio of the dose at a depth, at a point at depth D to what? The dose in free space. That dose in free space concept is not applicable for energies greater than cobalt-60. The reason is that even though you are measuring in free space, actually you have to measure in a mass that can provide uh, secondary electron equilibrium. Fine. So for that, you have to have, when the energy increases, you have to have thicker and thicker mass in order to provide that equilibrium condition. So when the mass becomes thicker and thicker, there will be attenuation. So you cannot allow that attenuation. Then the concept becomes invalid. That is the reason that it is not valid. The dose in free space concept is not valid beyond 1.25 MeV.
Okay. One interesting question is that, sir, what is equation to find the equivalent square field when we are putting a shield block in the center of the field?
I think that depends on the how much area that you are going to shield and what is the total area of the open field. Anyway, if you don't account for that, the PDD will not differ by more than a percent or 1.5%. You get my point? So even if you don't apply the shielded area correction, the PDD will not differ that greatly. What you have to do is to find out the output for the fully open field. Okay, output you have to taken for the collimator opening, but PDD, what you have to do, total area minus shielded area. So you will get the remaining area, and for that remaining area, you can find out area by perimeter. So area by perimeter multiplied by 4, that is the side of the square for that shaded field. And for that shielded field, you can find out the PDD for that reduced field size.
Yeah. Then again, we have questions about SSD technique. Two questions back to back. One is that why we use 100 centimeter SSD in LINAC and 80 in Cobalt, and why it is fixed at 80 or 100, not lesser, I mean 50 or 60.
See, like in Cobalt, it is 80 centimeter, that is the isocenter, and in LINAC, 100 centimeter is the isocenter distance. So if you are going to keep the SSD 80 centimeter, 100 centimeter, then it becomes easy for finding out many of the dose functions and correlating the dose that a physicist does with his chamber or her chamber to the dose at the different points. So if you are going to treat at different SSDs, say like not 80, 70 or 60, or not 100, 90 or 110, no problem, you can do that. What only thing is that you become vulnerable to commit mistakes, right? So that is why we keep the SSD equivalent to the isocentric distance. In that way, the possibility for committing errors become less.
Okay. And someone has asked to repeat the photon energy and the energy spectrum difference with depth.
See, a 6 MV beam will remain 6 MV whether at 1 centimeter depth or 10 centimeter depth or 15 centimeter depth or at 30 centimeter depth. Even after traversing 30 centimeter depth, a 6 MV beam will remain a 6 MV beam only. The energy of the beam or energy spectrum of the beam will not change. That's what I meant.
One question from YouTube is that how can we find our TPS surface dose is okay or not uh, for 6 MB or 15 MB?
I told you there are many uncertainty factors related to uh, TPS dose calculation for surface dose. The best way is to go to your machine, use some good measurement technique like TLD or MOSFET or OSLD. Using that, if you have calibrated them properly, then you will be able to measure the surface dose. But the TPS dose modeling is extremely poor. Do not depend or do not take any clinical decisions based on the uh, surface dose as reported by the TPS.
So last question from is that why does hydrogen have high electron density?
That's because, see, like you take the uh, hydrogen atom, right? In hydrogen atom, there is only one proton and one electron. There is no neutron in that. Fine. So for every one electron, there is one this one
Proton.
a proton. But in other atoms, you have got neutrons are also there, and that is why the electron density is less for other. So in hydrogen, for every electron, you have got one uh, uh, so for every proton, you have got one electron.
Dr. Srodha, you have asked when we'll use SSD and when SAD. That is also that is also already answered. And I would like to just tell one thing. I think someone has asked where he is not receiving the links in a regular basis or for each class. We have sent mail to all of you with the classes Zoom ID and password, which will be remaining same for all the classes. And we're not going to mail or give notification before every class. Thank you. Okay. Sir, thank you for your wonderful presentation. I think we have completed all the question answers here.
Just I wanted to tell all the participants, so those who are still left out, so you can, if you have got more questions, you can WhatsApp, not necessarily questions from this chapter. If you want, if you have doubt in any doubt in physics, you can ask me anytime. You can just mail me, you can WhatsApp me. What I will do, I will try to build a question and answer session, and then you can refer to that.
Thank you.
Thank you very much, sir. I have
Thank
been
you.
doing this. I have been asking many a times Dr. Ganesh whenever I am in doubt. So you can always do that. And he is always so helpful, and he will always answer our questions. Thanks very much, sir.
Thank you. Thank you.
For all the attendees, Zoom ID and password remain same. So use this Zoom ID and password for all the classes, and schedule has been sent to everyone. Thank you. Good night.